once again, BC Calc students, Mr. Record here from Avon High School, and we're taking a look at our example 2 from Larson's 9th edition, chapter 9.9. In this situation, we've got a power series, or a function rather, 1 over x that we want to center at 1 and find a geometric power series representation for. And of course, then we're going to state the interval of convergence like we would do with most of these series. And the issue here initially is that what we want, if you recall, is a form that looks something like this, a divided by 1 minus r. We talked a little bit about this in the last video that I did over example 1. And at the same time, we want this f of x function, this f of x, to sort of have that centering look at 1. And the most often way that we could express that centering at 1 would be to look at the binomial x minus 1. But all the while, we've got to make sure that we preserve the value of this function. We cannot change the fact that it is going to have to be equivalent to 1 over x. Otherwise, we've completely found a power series expansion for a different function. So it does just require a bit of trickery, I suppose. And I think the way to kind of start everyone off here is to utilize the 1 numerator. I think it's pretty clear that 1 will most likely be our a, and then just plop down a 1 minus. I mean, after all, we want it, right? We want this particular piece to lead things off with us. Now we want this x minus 1 binomial to stick around, but we want it to simplify with this 1 minus in such a way that it would ultimately be equivalent to 1 over x. And the best way to do that is to recognize the fact that we've already got a negative sign out in front of the parentheses, so why not just change the sign of each of the members of that binomial, and we would have a negative x plus 1. And if you look at this just a little bit further, you would notice that what is going on in this denominator? What do I actually have? Well, I'd have 1 distribute the negative plus x minus 1, which of course has our 1's canceling, which is our original x, which is exactly what we wanted. So we've got it made. We've got a representation where we can quickly and easily identify our value for a, which is 1, our value for r, which is, you could call it negative x plus 1, or you could swap things around and call it 1 minus x. I think that's what I'm going to do. And then we can write our power series like this. The summation as n goes from 0 to infinity of a, 1, I'll write that just for emphasis, times r, which is 1 minus x to the nth power. And this would certainly work. I have no problem with this particular representation. It's quite possible that this could be represented a little bit differently, and I want to warn you about that particular situation. In the case of, say, a multiple choice type of problem on the AP exam, notice that if we were to factor out a negative sign from that binomial, that negative sign would also have to be accompanied by a power of n. And in a nutshell, what we would end up having is that negative 1 to that power of n that would now be multiplied by the opposite of 1 minus x, which is now going to be what? Negative 1 plus x, or we could flip that around as x minus 1. And that would still retain that nth power. So you've got yourself an alternating series here, and although it may not have been readily apparent that that would be the case, but that is nonetheless what we've got. And if you were to throw in some values of n here for both of these, maybe I'll do that very quickly. If n is equal to 0, 1 minus x to the 0, of course, is 1. If I were then to throw n equal 1 in, I would have 1 minus x to the first, which is 1 minus x. And let's throw another one in here for good measure. If n is equal to 2, I would have 1 minus x squared. Do the same thing for this guy, throwing in n equals 0. Anything to the 0 times anything to the 0 is obviously 1. Now things will get interesting. If I let n be 1, I would have a negative and then quantity x minus 1 to the first. And then if I throw in an n equaling 2, I would have a positive 1, negative 1 to the second is positive 1, plus x minus 1 squared. And if you step back and compare what we've got here with our red and green representations, we would find out that we do indeed have the same thing. These two guys that I'm going to underline with one line are indeed equivalent once the negative is distributed through. These two guys with the double underlining might not initially look like they're true, but if you think about it for just a moment, we've got the commutative property at play here with a minus sign, which is never a good thing, but when you're squaring that result, all bets are off because we've got ourselves a positive result no matter what, and so those would be equivalent. So we've got a power series represented one of two ways, however you would prefer. And then to go ahead and figure out the interval of convergence, it might be just as easy to use this first representation since it's got that true geometric flair to it. So I'll take the r value of 1 minus x, work over here, and we would just set that less than 1. And then you go through your process of rewriting it as a compound inequality, subtract a 1 from all three sides, multiply or divide each side by a negative. Whoops, don't want this in here, right? That's a bad thing. Negative times 0 is just 0. And then, of course, the inequality symbols are going to flip, which gives us something that truly makes sense. 0 less than x is less than 2. And because this was a geometric series, we don't need to check the endpoints. So there it is, example 2, another power series represented as a geometric series. Hope this helps.